Okay. All right, so here we go. Suppose that we have a series, and this is actually an infinite series. Notice n goes from 1 to infinity, where we're going to try to add together an infinite number of terms. So this is an infinite series. We're going to be asked together, to try to evaluate this series by seeing if this infinite sum exists. That's really amazing when you think about it, because we're adding together an infinite number of terms where there really is no end into the number of terms that we're adding together. And it seems mind-boggling to think that anything like this could have a sum. When you think of when we keep adding values to it, how could it ever give us an actual finite sum? But some series do, but some don't, like this. We call this an infinite series. And although we're not literally going to add an infinite number of terms together, because to do so, as Owen, would mean that we would have to spend the rest of eternity to do so. And we don't have eternity, especially out here on Earth. Okay, so we can't do that. So what do we have to do here? Well, we have to ask ourselves if the sum of if this infinite sum approaches some value. Okay, so the question we want to ask ourselves is, does this infinite sum approach some value? And this word approach is also used as you begin to study the limit in your first semester of calculus. Okay, so does this infinite sum actually approach some value? In other words, does the sequence of partial sums approach some real number L as n approaches infinity? Okay, so in other words, as we allow the number of terms that we add up in our sequence of partial sums to approach infinity, in other words, as we add up more and more and more terms, ultimately allowing ourselves to add together, theoretically speaking, an infinite number of terms together, does this partial sum tend to settle down or approach some limiting value, L? If it does, then we say the series converges. Then we say that this infinite series converges. And we call L the sum of this infinite series. If our sequence of partial sums S sub n does not approach some value L as n approaches infinity, then we say the series diverges. And the infinite sum the infinite sum does not exist. Okay. So whether or not this infinite sum actually exists really depends upon whether the infinite series is convergent or divergent. And you look at this concept of convergence and divergence again in calculus, again, when you work with the limit. All right. Let's take a look at a specific example now. Let's consider the following geometric sequence. And this is the geometric sequence: 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128, 1/256, 1/512, etc., etc., etc. Okay. So this is an infinite geometric sequence. And the infinite associated series: 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1/128 plus 1/256 plus 1/512 plus on and on and on. So this is called an infinite series. Ladies and gentlemen, does this infinite series possess a sum? Does the sum of this infinite series exist? Well, in order for the sum of this infinite series to exist, this has to be a convergent series. Is it a convergent series? I don't know. Is it even is this even this is a geometric sequence, so this must be an infinite geometric series. All right. The question is, does the sum of this infinite geometric series exist? Well, let's argue that it does exist this way. Let's take one whole pizza or one whole pie. Let's subdivide this in half. There's 1/2, and here's the other 1/2. We're now going to take this, we're going to take one of these halves and subdivide one of these halves in half again. So now we have 1/4 here and we have 1/4 here. I'm going to take one of these 1/4, this one here, and I'm going to subdivide it again in half. So now I got 1/8 here and I have 1/8 here. I'm going to take one of these 1/8 and subdivide it further in half. So now I got 1/16 here and I got 1/16 here. Then I'm going to take one of these 1/16 and further subdivide it in half, this one. And half of 1/16 is 1/32. So now I got 1/32 here and I got 1/32 here. I have a question. How many times can I keep subdividing these pieces in half? How many times can I keep subdividing these pieces in half? Anybody? I mean, can I subdivide them only 20 times in half, 30 times, 40 times, 50 times? How many times can I continue the subdivision in half of these pieces?
Infinite.
Yeah, infinite number of times. You're exactly right. There's no end to how many times we can keep subdividing these pieces in half. Now, granted, the pieces are going to get smaller and 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 smaller. But as we continue to subdivide these pieces in half, not only are they going to get smaller, but we're going to start to see that there's going to be more and more and more of them, albeit smaller slices of them. Okay, so an interesting phenomena is occurring here. Now, I have a question for you. If I was to take all of these pieces, okay, all these fractional pieces and add them together, what would the sum of all these fractional pieces have to sum up to? What would all these infinite fractions have to add up to? And there'd be an infinite number of them because the pieces are being subdivided constantly in half. But nonetheless, even though there's an infinite number of times we can continue to subdivide these pieces in half, what would they have to all add up to? Anybody want to take a wild guess?
360.
Well, yeah, 360 degrees is all the way around the circle, but I think somebody else said something else when you said that. What was the other thing?
1.
That's right. Ladies and gentlemen, look at this. Isn't this one whole pizza or one whole pie? So I know this sounds bizarre, and it's actually mind-boggling when you think about it. But no matter how many times we continue to dice these slices up into smaller and smaller halves, and there's an infinite number of times we can do that. But granted, you got to admit, when you get back and look at the big picture, there is only one whole pizza or pie here. So when you do add up all these infinite, little slices, it better sum up to one whole pie or pizza. It has to. It cannot be any more because all these slices are contained within one pizza or one pie here. So that's right. So when you continually add all these up, the infinite sum, as bizarre as it may seem, has to be equal to positive 1. So this sum has to be 1, this infinite sum. In other words, we say that the sequence of partial sums that we touched base with on a couple of days ago approaches 1 as the number of slices approach infinity as we continue to subdivide the slices in half. The number of slices, therefore, will approach infinity, but the sequence of partial sums of these ever-increasing smaller and smaller fractions will approach 1. Because the sequence of partial sums approaches 1 as n approaches infinity, the number of slices approach infinity, we say that this infinite sum is equal to 1. That's what we say. So therefore, ladies and gentlemen, this must be what kind of an infinite series? Convergent or divergent? This is this turns out to be it's a convergent series. It's convergent. Okay, it's a convergent series. Convergent infinite geometric series. That's what that is. I have a question. What is the common ratio of the associated infinite geometric sequence? What is the common ratio here? What is the common ratio? What do I have to multiply each term by to advance to the next term?
1/2.
1/2. You are correct. The common ratio is 1/2. The common ratio of the geometric sequence is 1/2. Here's another good question. What does 1/2 raised to the nth power approach as n approaches infinity? What's happening to these terms of this geometric sequence, this infinite geometric sequence? Are they getting bigger or are the terms getting smaller? And if they're getting smaller, what do they appear to be approaching? What value do they appear to be approaching?
0.
That's right, 0. Isn't that true, ladies? Check it out. Look at it. Look, the denominator keeps growing without bound in these fractions, but the numerator is stuck at 1. And when you keep dividing 1 by a larger and larger and larger and larger denominator, the value of these fractions have nowhere to go but to approach 0. These terms are approaching 0. So in large part, you can see why this infinite series is a convergent infinite series, and it does converge to a literal finite sum value of 1, because the terms of the associated infinite sequence are convergent themselves. These terms are getting smaller. Granted, yes, we keep adding till the end of time or eternity, more and more terms, but these terms are getting so small once we get way out here that their contribution to the sum we've already accrued is becoming smaller and smaller and smaller and smaller of a contribution. So we say, therefore, that this sequence of partial sums, as n approaches infinity, is approaching 1. And that's enough then to jump off the cliff of faith and say, okay, if we were to theoretically continue to add an infinite number of these terms to all eternity, yes, the sum would be indeed 1. Okay. All right, so how does this tie into infinite geometric sequences and the formula that we're aiming at? Well, this is what we've discovered, and this is true. If the common ratio of a geometric sequence is a fraction that lies between 1 and -1, if R is some fraction that lies between 1 and -1, in this case it was 1/2. Say it's like a fraction of 2/3 or 3/5, or maybe -1/2 or -3/4. Okay. Then, ladies and gentlemen, we say that this infinite geometric series converges. Converges. The common ratio has to be a number between 1 and -1. No, has to be. Therefore, this infinite series will converge to an actual sum value. What if the common ratio is not between 1 and -1? Then will that infinite series converge or diverge? Well, I'll tell you what. Let's consider this case real quickly here. Suppose I had a infinite geometric sequence where these are the terms. Right? What's the common ratio of this infinite geometric sequence? The common ratio here is 2. And notice 2 is not in the interval between -1 and 1. So I have a question here. Would this infinite geometric series converge, or would it be divergent? What do you think? Intuitively, what do you think? What do you think? Do you think this sum, as we continue to add more and more of these terms together, is this sum ever going to settle down towards any specific number or value?
No.
Doesn't look like it at all. In fact, ladies and gentlemen, what's happening to these terms? They're not getting smaller. They're getting what? They're getting larger. These terms are growing. They're growing fast. And when you keep adding a larger and larger number to an ever increasingly larger and larger sum, that sum's only going to get larger and larger and larger. There's no way this infinite sum exists. So we would call this a divergent infinite geometric series. And so there you go. So for an infinite geometric series to converge, or in order for it to have an actual sum, what must be the condition? The condition is the common ratio has to be what? it has to be a fraction. And it has to be a fraction that lies between 1 and -1. Notice the common ratio cannot actually even be equal to 1 or -1. It has to be literally a fraction in between 1 or -1. So that's the only way an infinite geometric series could ever converge to a sum. If that common ratio is not a fraction in between 1 and -1, then that infinite geometric series will not converge, it will diverge. Diverge means it keeps getting larger and larger, larger, and growing without bound, we say. It grows without bound. Okay. All right. So what we've discovered is that our common ratio has to be a fraction between 1 and -1 in order for our infinite geometric series to be convergent, in order for an infinite geometric series to have a sum. Okay. So let's look at our finite sum formula we developed last week, a couple days ago. The sum of the first n terms of a geometric sequence. I believe this was the formula that we hammered out, correct? Everybody see that there? So I have a question for you, ladies and gentlemen. If our common ratio for a geometric sequence is a fraction that's between 1 and -1, then what does r to the nth power approach as n approaches infinity? Remember, r has to be a fraction between 1 and -1. So it has to be a fraction less than 1 and greater than -1. What happens to that fractional value as we raise it to a larger and larger power? What happened to that 1/2 common ratio as we raised it to a larger and larger power? It approached what? 0. And that's true for any fraction that is between 1 and -1. When you raise it to a larger and larger power, as you allow the exponent to approach infinity, grow without bound, then that fractional value that you're raising to that larger and larger power will approach always 0. And therefore, what happens to this guy in the formula? As n approaches infinity, this term approaches what? 0, and essentially drops out of the picture. And so, as n approaches infinity, the sequence of partial sums n approaches a sub 1 times 1 minus 0 over 1 minus r. Well, since our sequence of partial sums is actually approaching this value as n approaches infinity, we would say then that the infinite sum is equal to this value. And ladies and gentlemen, we have developed the infinite sum formula for a convergent geometric series. That formula is pretty important. That enables you to crank out the sum of any convergent infinite geometric series. It has to be convergent though. So what has to be the requirement on R again? R has to be what? R has to lie between 1 and -1. This has to be the case. Otherwise, you cannot even use this formula. There would be no sum to the infinite series if R does not lie in here, this interval. Now, another way to represent this interval that textbooks do represent it this way, they use the absolute value of R as less than 1. To say the absolute value of R is less than 1 is saying this. This is another way of implying this interval. This is a more compact way of implying this statement. Okay. All right. There's your infinite sum formula for a convergent infinite geometric series. Let's see if we can put it to use. Okay. Any questions about this here? All righty. All right, let's see if we can evaluate this infinite series then. I equals from 1 to infinity. It doesn't matter what you call your index of summation. You can call it n or I or k or j or anything, right? Doesn't matter. But generically, This is always the nth term rule though. Despite what you call your index of summation, what letter you use, this is always your nth term rule for the terms of the sequence. This is your nth rule. So I have a question for you, ladies. What would be the first term? What would be the first term of this series or sequence? The first term. Well, the first term is established by letting I be what? 1, correct? So we would have 5 times negative 1/3 raised to the 1 minus 1 power. Plus the second term would occur when I is 2. That'd be 5 times negative 1/3 raised to the 2 minus 1 power. Plus on and on this goes. So the first term of the associated geometric sequence, or the first term of this series here, would be 5 times negative 1/3 to the 0th power. But negative 1/3 to the 0th power is 1, and 1 times 5 is 5. That'd be your first term. Your second term would be what? Negative 1/3 raised to the 2 minus 1 power is negative 1/3 to the first power, which is negative 1/3. Times 5, which would be negative 5, what? Negative 5/3. Then if I is 3, your second term would be negative 1/3 to the 3 minus 1 power, negative 1/3 squared, which would be positive 1/9 times 5, or 5/9. So it appears we have an infinite alternating geometric series here. Alternating because the signs keep alternating. All right. Positive, negative, positive, negative, positive, negative. Nonetheless, what is the common ratio of this infinite geometric series? What is the common ratio? Well, the common ratio can be found by taking any term and dividing by its predecessor, the previous term. And so the common ratio is negative 1/3. In fact, the common ratio is staring at us right here. Because remember I said this is the nth term rule? So this is really the nth term rule of a geometric sequence. It's a sub n is equal to 5 times negative 1/3 raised to the n minus 1 power. That's the nth term rule. And ladies and gentlemen, this is R. R is negative 1/3. A sub 1 is 5. Wasn't that how the rule went 2 days ago? You agree? The nth term rule for a geometric sequence? Your first term is 5. Your common ratio is negative 1/3. So you don't even have to list the first couple of terms to determine what your first term in R is. You can basically just pick it right out of the summation nth term rule right here. All right, now, does negative 1/3 lie between 1 and negative 1? And the answer is yes, it does. Because my common ratio lies between 1 and negative 1, this is a convergent infinite geometric series. And because it's a convergent series, this infinite sum must exist. And so what is it? Well, to find what it is, we use our infinite sum formula we just developed. This has got to be equal to our infinite sum of our, this is equal to the infinite partial sum, which is equal to the first term divided by 1 minus R. Our first term of which is 5, common ratio is negative 1/3. All we got to do is just crank this out and we have our infinite sum. So it's going to be 5 over, this is 1 plus 1/3. 1 plus 1/3 is 4/3. So we're going to have 5 divided by 4/3, which is going to be 15/4. And there you go. That's your infinite sum, 15/4. So that's what adding an infinite number of those terms together is going to give us. This sum, which as a mixed number is going to be 3 3/4 or 15/4. Any questions how we evaluated that infinite convergent geometric series? So we use the infinite sum formula to evaluate that. Okay. All right. Let's try another one here. 2 plus 8/3 plus 32/9 plus 128/27 plus ... This is an infinite series. Is it a geometric series? What's the common ratio? Does there exist a common ratio? Is 8/3 divided by 2 equal to 32/9 divided by 8/3? Is that equal to 1/28/27 divided by 32/9? Is that true? Is there a common ratio here? And if so, what would it be? So what's my common ratio? Well, 8/3 divided by 2, I think it's going to give us 4/3. Common ratio is 4/3 here. Now, is R equal to 4/3 in the interval -1 to 1? Is 4/3 found in this interval?
No.
No, this is bigger than 1. This is 1 1/3. The answer is no. So this infinite series does not converge. It diverges. And since it diverges, this sum does not exist. Sum does not exist. So we're wasting our time in trying to find it. You cannot even use your infinite sum formula. Can't use it on this one. That's a divergent infinite geometric series. So don't try to use the infinite sum and try to crank out a sum because it has no sum. So it has to be a convergent geometric infinite series in order to use that infinite sum formula. And in a way, it kind of makes sense because it kind of looks like these terms are getting bigger and bigger and bigger, correct? And you're adding larger and larger terms. And so it seems like, yeah, this sum would never really settle down to any value. And it would just keep getting larger and larger and larger and grow without bound. And that's why we say the infinite sum simply just does not exist. Okay. All right. Here's an interesting application of these infinite convergent geometric series. What does this decimal mean here with this bar above here? What is that? How do we interpret that decimal there with that bar above the 5? What's that saying?
5 repeating.
This is called a repeating decimal. And the digit that repeats is the digit that the bar is above. So this is really equal to 0.55555, and this 5 goes on forever. Called repeating decimal. What if I want to take this and do something interesting with it? Suppose I want to write this decimal as a fraction. How would we do that? How would I write this decimal as a fraction? Now look at, if I just had 0.5, well, this is a terminating decimal. To write it as a fraction is trivial because this is just 5/10. 5/10 or 1/2, done with problem. Agree? Well, how do you do this? How do you write, how do you write that repeating decimal, ladies and gentlemen, as an equivalent fraction? What do you divide? What number do you divide by what number to give you this repeating decimal, 0.55555? To the rescue is the infinite convergent geometric series. That's going to enable us to take care of this. Watch this. Do you agree that this repeating decimal, I can write it like this. I can write it as 0.5 plus 0.05 plus 0.005 plus 0.00005 plus 0.00005 plus on and on. This can go forever. Do we buy that? Does that make sense? That nifty? Sure, that would be true. Now, this is a series. Is it a convergent infinite series, though? And is it geometric? Well, how do I write this as a fraction? 0.5. Well, I showed you above here. It's just 5/10. So this is 5/10. This is 5/10. How do we interpret this? 5/10, hundredths. This is 5/100. 5/100. Plus, how do you interpret this decimal? How do you read it? It's 5/10, hundredths, thousandths, 5,000. 5/1000. How do you read this decimal? Tenths, hundreds, thousands, 10,000s. This is 5/10,000. And on this goes forever. That makes sense? I have a question for you, ladies and gentlemen. Is this a convergent, infinite, geometric series? What would be the common ratio? What is the common ratio here? What is the common ratio? What do you got to multiply each term to move to the next term? What do you multiply 5/10 by to move to 5/100? Or what's 5/100 divided by 5/10? What does that give you? Well, after doing this, it looks like the common ratio is going to be 1/10. But notice 1/10, the common ratio lies between 1 and -1. So is this a convergent infinite geometric series? The answer is yes. This is a convergent geometric series. And since we're adding together an infinite number of terms to evaluate the sum of this infinite geometric series, we use the infinite sum formula. So 0.555555 that repeats forever is really equal to the first term of this series divided by 1 minus the common ratio. But what's the first term? The first term is 5/10, either as a decimal or as a fraction. I'm going to write it as a fraction, 5/10. And that sits over 1 minus the common ratio is 1/10. What's 1 minus 1/10? That'd be 9/10. So what's 5/10 divided by 9/10? That'd be 5/9. You got your answer. I want you to convince yourself, Liz. Get on your calculator right now. Take out a calculator and divide 5 by 9. What's 5 divided by 9? Does that give you that repeating decimal? Does it work?
Yeah.
That's how you get the repeating decimal written as a fraction. You can use an infinite convergent geometric series to help you do that. And nifty. Now that was kind of an easy one, 0.55555. I'm going to show you another one that's a little bit more, not as easy as this one here, though. But that's how you would write that repeating decimal as an equivalent fraction, 5/9. All right, let's look at another one. Suppose that I have this repeating decimal, 1.975, where what digits repeat now? Only the 75. And therefore, this is really 1.975, 75, 75, 75, 75, 75, and this will go on forever. Suppose I want to write this decimal as a fraction. In other words, what number do you divide by what number to generate this repeating decimal? Well, here we go. 1.975 that repeats forever. Do you agree? I could rewrite as 1.9 plus 0.075 plus 0.00075 plus 0.0000075 plus on and on this goes. Do you agree? We could do this forever. All right, let's analyze this now. Well, this is saying what? This is 1.9 plus, you know what? I want to turn this 1.9 into a fraction here. So hold on a second. How do I write 1.9 as a fraction? Well, 1.9 is really 1 9/10, which as an improper fraction is going to be 19/10. So this is really 19/10. Now, how do we write this as a fraction? This is 75 what? Tenths, hundredths, thousandths. 75 over 1,000. How do I write this as a fraction? Tenths, hundredths, thousandths, 10,000ths, 100,000ths. This is 75 over 100,000. This is 75 over what? Tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions. 75 over 10 million. On and on it goes forever. Now, I don't care about my first term. I'm not going to involve it in my convergent infinite geometric series, but I am going to have to add it in the end. So I'm not concentrating on this part of the series. I'm going to concentrate later on this portion of the series, this portion of the infinite series, from this term on to infinity. Okay, so my question is this. What's the common ratio of this portion of my infinite series? The common ratio. What are you going to multiply 75 over 1,000 by to generate 75 over 100,000? What is my common ratio here? Well, if you take 75 over 100,000 and divide it by 75 over 1,000, you'll discover your common ratio is 1/100th. That's your common ratio. So, is this infinite geometric series convergent from this term on to infinity? The answer is yes, because my common ratio is a fraction that's between 1 and -1. So this portion of my infinite series converges. It converges. And so what is its sum? What is its infinite sum? Well, whatever its infinite sum is, we have to add it to the 19/10ths here. You can't lose that 19/10ths. So this is plus, now we use the infinite sum formula, which is to say we take the first term and divide it by 1 minus the common ratio. So this is really going to be 19/10ths plus, what's my first term of the infinite converging geometric series? The first term is 75 over what, 1,000, correct? 75 over 1,000 is my first term. Divided by 1 minus my common ratio is 1/100th. And now we just got to clean this up. We just got to clean this up and we will have written this repeating decimal as a fraction. So we have 19/10ths plus. Now, how do you clean this up? Well, this is going to be 75 over 1,000. And 1 minus 1/100th is 100 hundredths minus 1/100th, which is 99 100ths. This is the complex fraction. You could multiply top and bottom by the common denominator, which is to say multiply top and bottom by 1,000 to simplify this down to a simple fraction. Therefore, we have 19/10 plus, this is going to be just 75. When you multiply this together, this will be over 900 and what, 90? Is that correct? I believe. All right. And now you need a common denominator of both these guys here, and the common denominator is going to be 990. So that means you multiply this top and bottom by 99. And what's 19 times 99? This is all basic math here. 19 times 99 is 1881 over 990 plus 775 over 990, which 1881 plus 75 gives me 1956 over 990. And can this be reduced? Well, let's see. If nothing else can be reduced by 2, this immediately divided by 2, 2 over 2 gives you 978 over 495. Can you reduce this anymore? Well, 15, 24, let's see, 14, 18. You can reduce by 3. 978 divided by 3 takes us down to 326. And what's 495 divided by 3? 165. And I think that's his 12. Let's see, 8. That's as low as it's going to go. There you go, ladies and gentlemen. We've done it. Take your calculator now and convince yourself. Take 326 and divide it by 165. Does it generate that repeating decimal of 1.975757575757575? You got your answer. So we've rewritten this repeating decimal as a fraction. It's 326 over 165. That was a more complicated one, but we understand that, know what just happened? All right, so we're done with that problem and we're done with that section. So that closes out section 8.3. Finally done with 8.3. All right, now let's learn how to count. You're probably saying, what? Ladies and gentlemen, counting can be more difficult than you think. In fact, you could kill a whole 15-week semester course at a university called combinatorics. Combinatorics. Let me write that down. Combinatorics. It's a course that shows us how to count. And I think you will agree with some of these examples I'm about to show you that counting can be difficult. It's not as simple as we think. So to open up section 8.6, we are going to introduce ourselves to some very basic combinatorics, okay? No, this section isn't going to take 15 weeks. It better not. All right, so to do that, we're going to go to our textbook. So let's go grab our textbook. Let's see if technology will allow me to open up my textbook. All right, here we go. All right, so we're going to go grab our textbook. And I'm going to go to section 8.6. And 8.6 is entitled Principles of Counting. All right, we're going to begin with example 1. Check this out. Suppose that a frozen custard shop offers 4 flavors of custard.
2 types of syrup, and 2 toppings. If a customer can select one item from each group for a sundae, how many different sundaes can be possibly put together? Well, we got 4 different custard flavors: vanilla, chocolate, mint chip, and peanut butter. And we have 2 syrups: hot fudge, butterscotch. We have 2 toppings: nuts and granola. How many different sundaes can be constructed if we're able to choose only one type of custard, one type of syrup, and one topping? Well, to enumerate all the possibilities, we can use a tree. And this tree is going to be a tree that grows from left to right. The root of which is down here. You have 4 main branches emanating from the root. The type of custard: vanilla, chocolate, mint chip, and peanut butter. From each of those main branches, 2 more branches emanate: the type of syrup, hot fudge, or butterscotch. And from each of those smaller branches, 2 smaller branches emerge: the type of topping, nuts, or granola. And so, ladies and gentlemen, all you got to do is follow the branches of this tree to determine the different number of sundaes that are possible. You could construct a sundae that has vanilla, hot fudge, and nuts, or vanilla, hot fudge, and granola, or vanilla, butterscotch, and nuts, or vanilla, butterscotch, and granola, or chocolate, hot fudge, and nuts, or chocolate, hot fudge, and granola, or chocolate, chocolate, butterscotch, and nuts, chocolate, butterscotch, and granola, mint chip, hot fudge, nuts, mint chip, hot fudge, granola, mint chip, butterscotch, nuts, mint chip, butterscotch, granola, peanut butter, hot fudge, nuts, peanut butter, hot fudge, granola, peanut butter, butterscotch, nuts, peanut butter, butterscotch, granola. How many different sundaes are possible? Was anybody keeping count? Well, as I went to determine a number of sundaes that are possible, to the rescue is a very important principle of counting. It's called the fundamental principle of counting. It's embodied in this purple box here, which is in section 8.6 on page 739. The fundamental principle of counting says this: if one event, whatever the event is, can occur in m different ways, and a second event can occur in n different ways, then the total number of ways that the two events can occur in sequence would be m times n. That's called the fundamental principle of counting. So let's go back up to our example. Ladies and gentlemen, how many types of custards do we have available? We have 4 choices. How many choices for the syrups? 2 choices. How many choices for the toppings? 2 choices. What's 4 times 2 times 2? According to the fundamental principle of counting, there are 16 possible sundaes you can arrange. 16. And we have gone through all 16 by following the branches of the tree. Does that example make sense what's going on there? So we're starting to see, ladies and gentlemen, that counting may not be as easy as we think. Could you imagine if you had, are you ready for this? Suppose that instead of 4 different custards, 2 different syrups and 2 different toppings, could you imagine how this could start to get out of hand if we had 20 different custards, maybe 10 different syrups, and maybe 5 different toppings? Wow. Now this is going to be interesting. 20 times 10 is 200, times 5 is 1,000 different sundaes you could construct, 1,000 different ones. Care to enumerate all of them? Could you imagine the size of this tree to try to enumerate all the 1,000 possibilities of this situation here? we'd have to have 20 branches, in each branch branching out to 10 branches, and each of those branches branches out to 5 branches. Okay, that would be extremely difficult to construct from a humanistic point of view. But you know, computers are ideally suited for working with trees. In fact, later on, when I went through my undergraduate computer science regimen at U of M Flint, there's 2 things that I've learned about what computers do the best. Computers are ideally suited for doing what are called searching. Most algorithms and computer codes out there in the real world are search codes and sorting codes. To perform searches, the most elegant, efficient way to have a computer search for, let's say, an item in a warehouse that maybe has millions of items in it, is to build what's called a binary search tree. And you do study search trees in computer science and how to encode them using a language. Okay. Computers can run along these branches of this tree within a fraction of 1 second, even if there's millions of branches, doesn't matter. A computer can go through a tree in about a fraction of a second with our supercomputers nowadays. So it doesn't matter how big these trees get with computers, but with humans, it becomes a big issue because we are not able to handle the volume of possibilities as fast as a computer system can. All right, so that's example number 1 in your textbook. Okay. All right, let's look at this next example. And here it is. This is example 2 in section 8.6. A computer password must have 3 letters, let's say, followed by 2 digits. How many passwords can be made if A, there are no restrictions on the letters or digits, B, no letter or digit may be used more than once? Okay. Now, I like to think of this password consisting of little mailboxes. Notice we need to have 3 letters in our password, and we need to have 2 digits. Okay. Letters, digits. All right, we will assume that our letters are lowercase letters because most passwords have lowercase. I have a question for you. How many lowercase letters from the alphabet can occupy the first slot? How many letters are in the alphabet?
26.
26. How many letters could occupy the second slot of this computer password? Well, repeats are possible because for part A, it says there's no restrictions, which means we are open to the possibility of having repeated letters or repeating digits. So again, there's 26 letters that could occupy the second spot. There's also 26 letters that could occupy the third spot. How many digits could occupy the first slot here of the number portion of the password? Well, digits would be 1 to what? 0 to 9 are your digits. That constitutes 10 digits, either a 0 or a 1 or a 2 or a 3 or 4 or 5 or 6 or 7 or 8 or 9 goes in here. That's 10 possibilities for a digit. We could have repeated digits, so there's 10 possibilities for the last digit also. How many different passwords are possible? According to the fundamental principle of counting we just looked at, we would multiply all of these arrangements. So get on your calculator and tell me, what is 26 cubed times 10 squared? What does that give us? How many different passwords can we arrange? There's your answer. Now, what does that give you for a product? I don't have my scientific calculator. Let's see. I don't know if this Mickey Mouse machine is going to be able to handle that. Well, it did. It's a big number. It looks like 1,757,600 different combinations. Do you agree? For this password. Now, could you imagine if there's only one correct password, how long it would take for a human to go through all of these potential passwords? It would take a while. Now, computer systems, ladies and gentlemen, can go through this very quickly, but not a human. All right. Suppose now in part B that there is a restriction. The restriction says we cannot have repeated letters or digits. Let's do this over again now. How many different letters can I put in the first little mailbox here for my password? There's 26. But ladies and gentlemen, we cannot have repeated letters. That means I must keep one of these letters out for this slot here. Therefore, I only have 25 letters to choose from to occupy the second slot. But by now, I've kept out 2 letters, one for the first and second slot, which means I'm down to only 24 letters left to occupy the third slot. In the first digit slot, there's 10 digits possible to occupy this slot. But I left one of the digits out in the first slot, which means I only have 9 digits left to choose from to occupy the second slot. And there you go. This would be the total number of passwords that we could have for a computer system if we cannot have any repeated letters or digits. Do you think it's going to be more or less? The answer from A. Well, I think it's obvious that it's going to be what? It's going to be less. There's only 1,404,000 passwords possible for this situation where we cannot have repeated letters or digits. So is this fundamental principle of counting making sense? How if we have this many arrangements for the first, this many for the second, for the third, for the fourth, and the fifth, to find the total number of arrangements possible, we multiply these together. That's the fundamental principle of counting. That's what it's telling us. Okay. Making sense here so far? All right, let's go on to, and there's the answers, of course. The author worked out the solutions. Now let's go on to the next one. A quiz, example 3. A quiz has 5 true-false questions and 5 multiple-choice questions. Multiple-choice questions each have 4 possible answers, either A, B, C, or D, we'll say, of which only one is correct. If a student forgets to study for the exam and must guess on each question, in how many ways can the student answer the questions on this particular test? How many different ways potentially could this student answer all of these questions on this test if he or she purely guesses at each problem? Well, how many true false questions we got? We got 5, 2, 3, 4, 5. I only have 5 little slots or 5 little mailboxes for the true false questions. How many for the multiple choice questions? We got 5. 1, 2, 3, 4, 5. Okay. Let's find out, ladies and gentlemen, how many different ways we can answer this exam. So there's 5 true false questions, and there's 5 multiple choice. How many different ways can you answer question number 1 on the exam, being true or false? How many different ways? There's 2 different ways. You could answer either true or false. How many different ways could you answer question number 2, also being a true or false question? There's 2 ways. In fact, there's 2 ways to answer any one of these 5 true or false questions. 2 ways. How many ways can we answer a multiple choice question, each having 4 possible selections? There's 4 ways to answer each of these multiple choice questions. What's the total number of ways we could answer this 10-question exam? The fundamental principle of counting says to find that out, we would multiply all these arrangements together. So this is really going to be 2 to the 5th power multiplied by 4 to the 5th power. Let's get on our calculator and dial that up. That would give me 32,768 different ways to answer this 10-question exam. 32,768 different ways. And of all those ways, ladies and gentlemen, how many ways would produce a 100% score on this exam? How many ways represent a 100% score in this exam? How many ways?
One.
There would only be one lonely little way. Do you agree? To get a 100% score in this exam. So you know what the probability, and I'll give you a sneak peek of probability to come. You know what the probability of purely guessing at each of these 10 questions and getting every single one correct and getting a 100% on this exam? The probability is 1 divided by 32,768. And if you multiply this decimal by 100%, you will figure out the percent chance of scoring 100% on this exam. So I'm going to run this through quickly and find out. You got to be kidding me. This is like 0.003% chance of purely guessing and scoring 100% on this exam. That's only 0.003 of 1%. This is not even close to being close to 1% chance. That's minuscule. So yes, the chance of purely guessing, ladies and gentlemen, and scoring 100% is extremely rare, as you can see. Extremely rare. You have a better chance of probably just not even taking the exam. Do you agree? Yeah, so it's obviously wise to study a little bit for an exam. Okay, now, so we've seen how the fundamental principle of counting is enabling us to determine the total number of arrangements that are possible given individual arrangements for some sort of an event. Now we're going to look at some tools that can help us count. And these tools are found on our calculator. The first one is called the combination. Ladies and gentlemen, with combinations, order always matters. Order, wait a minute. No, strike that. With a combination, order does not matter. That's what I meant to say. And you'll see what this is all about in a moment with an example. Order does not matter with combinations. Suppose I have 4 people. Ben, Sue, Jane, and Troy. B for Ben, S for Sue, J for Jane, T for Troy. And from these 4 people, suppose, ladies and gentlemen, I want to determine how many teams of size 2 can be arranged. Suppose maybe, we're gonna have maybe a volleyball tournament. How many different ways can I choose teams of size 2? Or maybe it's like doubles tennis match or something, okay? I got a question for you. Does it matter in which order I choose these people to form my teams of size 2? In other words, does it matter if I choose Ben first and then Sue second to be on a team? Or if I choose Sue first and then Ben second to be on the team? Do you think order matters here? Do you think order matters? Absolutely what? Absolutely not. Order does not matter, ladies and gentlemen. Whether we have the team of Ben and Sue or Sue and Ben, it's still the same team, same 2 people. So let's find out how many different teams of size 2 are possible. Well, I could choose Ben and then Sue. Why do I not count the team of Sue and Ben? Because these are the same teams. Order does not matter here. Don't count it. Ben and Sue. Now watch how I'm going to keep this organized. I could choose Ben and Sue, or I could choose Ben and Jane, or I could choose Ben and Troy. We're done with Ben. Move to Sue. Sue and Jane. Sue or Jane. Or Sue or Troy. Done with Sue. Move to Jane. Or Jane or Troy. There you go. Those are all the number of teams of size 2 I could choose from these 4 people. How many is that? 1, 2, 3, 4, 5, 6. There's 6 teams possible I can put together here. Ladies and gentlemen, this is called the combination. This situation here, where order does not matter in choosing these teams or putting these teams together. And to the rescue, we have this formula. And in combination with R, or N choose R. That's how we read this notation. N in combination with R, or N choose R. Formula does make use of factorial, the factorial function, which we touched briefly on when looking at some sequences of series 2 days ago. This is equal technically to N factorial divided by R factorial times N minus R quantity factorial. That's called the combination formula. Now, the good news is we don't even need to dabble or play around with the factorial function, because you got this baby built right into your calculator. In fact, ladies and gentlemen, if you hit your math button, you go over to your probability menu, PRB, short for probability, then you can see that you would have the NCR function down there. Let's put it to work to show ourselves that there's 6 possible teams of size 2. N is the total number of things we have to choose from. So in this case, with my example, I had 4 people to choose from. N would be 4. R represents how many from all the things we have to choose from we actually choose. So I'm choosing 2 people from the 4 people. So 4 in combination with 2 would generate the total number of teams that are possible. So how do we bring this up on our calculator? 4 choose 2, or 4 in combination with 2. By the way, some textbooks use a different notation for the combination function. Some textbooks use this notation. This notation means the same thing as this. So in general, some textbooks use this notation for combination. Some textbooks use this notation. These mean the same thing, these notations. All right, how do we do this on our calculator? Well, let's go find out. So we clear our screen on our machine. All right. So clear your screen, type in what N is, 4. And now we got to go get the combination function. So 4, math, go over to probability. Whoops, probability, and then go down to probability, and then select what? NCR. There you go. Now you got to type in what R is. R is 2 in this case. Hit enter, boom, you get 6. Any questions how I computed the number of ways of forming a team from a group of 4 people if order does not matter? There's 6 possible teams that are constructible. All right, done on that. That's how you use your combination formula. Okay. What if order mattered? In this situation, in selecting these teams of size 2, we didn't care in what order we selected our 2 people. But what if order matters? What do we do in a situation like that? Well, in that situation, ladies and gentlemen, we have to use what is called a permutation, not a combination, but a permutation. A permutation, with permutation, order matters. Order matters. Let's use our same examples here. We used it before. We had Ben, we had what? Sue, Jane, and we had what? Troy. Okay. Suppose now I'm trying to form maybe a student body governing committee of size 2, where I must select a president and I must select a vice president. Got a question for you, ladies and gentlemen. Do you think order matters now? Does order matter now? Well, it certainly does. May mean a huge difference in your paycheck as to who's president, who's vice president. So order does make a big difference now. It matters. And therefore, what are the number of possible ways of forming this political committee of size 2? If I got 2 candidates, 4 candidates rather, to select from. Well, I could choose Ben to be president and Sue to be vice president. Or I could flip this around. Sue could be president, Ben could be vice president. Or I could choose Ben to be president, Jane to be vice president, or Jane to be president and Ben to be vice president. Or I could choose Ben to be president, Troy to be vice president, or Troy to be president, Ben to be vice president. Or, ladies and gentlemen, we're not done. There's more. I could choose Sue to be president and Jane to be vice president, or Jane to be president, Sue to be vice president. Or I could choose Jane to be president and Troy. Wait a minute here. Sue and Jane. Jane and Sue, or, no, hold on, I want to keep this organized here. If you don't keep this organized, it's going to come unglued fast. So I was working on, let's see, Sue and Jane. Okay, so Sue could be president, Jane vice president, Jane could be president, Sue vice president. Or I could select Sue to be president and Troy to be vice president. Or I could select Troy to be president and what? Sue to be vice president. Or, ladies and gentlemen, I could select Jane to be president, Troy to be vice president, or Troy to be president, Jane to be vice president. How many different possibilities is this here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 possible political committees that I could form, where one is president and the other one is vice president. 12 different possible committees. Now, how to give us that number 12? Well, this is a permutation. And to the rescue is what's called our permutation function. And permuted are ways. That's how you read that notation, ladies and gentlemen. And permuted are ways. This function is on our calculator. If you're wondering how the function works, it makes use of the factorials. This is really n factorial divided by n minus r factorial. How is this formula different than the formula for a combination? Does anybody want to weigh in on what the difference is? Remember, this was the formula for the combination here. There's one subtle but very important difference. What is it between these two formulas? What is the difference? Well, the difference is with the permutation formula, you don't see r factorial in the denominator. And therefore, which denominator would be bigger? The permutation or the combination denominator? What do you think? Which denominator would be larger? As it turns out, the combination formula denominator is larger than the permutation formula. And because of that, the combination value is always going to be less than the permutation. So this is always true. A permutation is always greater than a combination. And you can clearly see it in this example. There's 12 possible committees of size 2 where we have a president versus vice president, as opposed to only 6 possible teams of size 2 where order does not matter. So whether order matters or does not matter makes a huge difference. All right, any questions about combinations or permutations here so far? Let's go to our textbook and have a little bit of fun. So what I'm going to do now is I'm going to go down and we're going to look at a couple problems here. I want to go down and look at problem 52A. So let's scroll on down. (52A). (52A), how does it read? It says there are 100 members of the U.S. Senate. Suppose that 4 senators currently serve on a committee. The question is, in how many ways can 4 more senators be selected to serve on the committee? You think order matters? In which does order matter in how we select these 4 remaining senators to serve on this committee of size 8? Think order matters? The answer is absolutely not. Doesn't matter. We just got to select 4 more senators to be on this committee. So I guess all the members on this committee are of equal rank. Well, order does not matter. And because order does not matter, are we talking about a permutation or a combination? We're talking about a combination. All right, and so therefore, how many senators do I have remaining to select 4 from? Well, 100 senators total in the Senate, but 4 have already been selected for the committee. That leaves 96 centimeters, 96 centimeters. That leaves 96 senators left to select the 4 remaining vacancies. So of the 96 senators remaining, I have to select 4 where order does not matter. And so therefore, for problem 52A, the number of ways of selecting the 4 remaining senators to serve on this committee of size 8 is 96 choose 4 or 96 in combination with 4. So we'll get on our calculator and hopefully we can dial that up. And what do we get? We get a big number. 3,321,960 different ways to select the remaining 4 senators. You know, when I see all these ways here, I'm thinking of that Snickers commercial, which you don't even see on TV anymore. But anyways, it always says gonna be a while. Okay, yeah, this is gonna be a while. We only have 3,321,960 choices. That's all. This making sense? All right, let's go do 52B now. Problem 52B. It says, in how many ways can a group of 3 US senators be selected from a group of 7 senators to fill the position of chair, vice chair, and secretary? Well, does order matter now? In how we choose these 3 senators from 7 senators to fill these 3 different offices? Order matters, because whether you are selected for the chair position or the vice chair or the secretary position could mean a huge difference in your paycheck, for one thing. Order matters, ladies and gentlemen. So therefore, since order matters, what am I going to use? Permutation or combination? So now we're going to have to turn it over to the permutation, where we have 7 senators to select from, and we have to choose 3 of them to fill these 3 offices. So we're going to use not the combination function, but we're going to use the permutation function. So this is going to be 7. That's going to take forever to dry. 7 permuted 3 ways. Get on your calculator and dial that up. By the way, your permutation hangs out in the same area where your combination hangs out. So you have to hit your math button, go over to probability, you go down and grab the NPR function. 210. There's 210 different ways to fill these 3 offices. 210 different ways. That's even going to take a while. All right. Any questions about any of these problems here so far? Okay. Let's go back to our textbook and look at like number 56 now. Number 56, in a New York State lottery game, Lotto, a player wins the grand prize by choosing the same group of 6 numbers from 1 through 59, as is chosen by the computer. How many 6 number groups are possible? Ladies and gentlemen, think of it as we got 59 balls bouncing around in an urn. Kind of like, anybody play bingo? You and me are good company, ladies and gentlemen. I played it a couple times enough to know that it's not for me. In fact, I am convinced that if I was the last person on planet Earth and there was a bingo game, I still could not bingo. Still couldn't bingo. Okay, that's how bad it is. So in other words, we got 59 balls bouncing around. Each ball has a number on it, 1 to 59. Okay. If we randomly select 6 of these balls, 6 numbers, okay, how many different possible arrangements are there to select a 6-digit ticket for this game here? Well, does order matter when we play the lotto or the lottery game? You can tell that I play the lottery or the lotto a lot, which I don't. So you're going to have to help me out here, ladies and gentlemen. Anybody play the lotto or lotto game, lottery, lotto, or grand mega drawing or whatever it is out there? Anybody? Does order matter in which you choose your numbers on your ticket?
No.
I don't know. When I had my face-to-face section this morning, they said that it doesn't matter either. So I guess order doesn't matter. As long as you just choose, the 6 correct numbers in any order, you win the jackpot. Okay. Well, how many different ways from 59 numbers can you choose 6 numbers? Well, since order does not matter here, we're talking about a combination. So order does not matter. So therefore, the number of ways that you could form a 6-digit ticket would be 59, choose 6, or 59 in combination with 6. Let's go dial it up. Go get that function to see what it is. Just as I suspected, a horrendously large number. There's 45,057,474 different 6-digit tickets, ladies and gentlemen. And how many of this massive number of tickets is the winning ticket? How many are the winning tickets? I mean, we're talking the jackpot, the grand, the grand prize, where you can get yourself on that series with that guy that sells, he sells the lotto winning reality show. I don't know. You know, if you win the lotto, you go with this guy, he'll show you all these houses and you can pick out which house you want or whatever. Anyways, how many tickets are the winning ticket here?
One.
One. So what's your probability of getting the right ticket? 1 over, you ready for this? 45,057,474. Work that decimal on your calculator, multiply it by 100%, and you have your probability or chance of winning that lotto. So what is 1 divided by 45,057,474? It's small, times 100%. Oh my gosh. Look at this. I'm getting 0.12345 chance of winning this lotto game. Ladies and gentlemen, 1% is way up here. This is tenths, hundreds, thousands, 10,000s, 100,000s, millions. You got 2 billionths of 1% chance. 2 billionths of a 1% chance of winning this lotto with one ticket. Even if you buy 100 tickets or 1,000 tickets or 10,000 tickets, your chance of winning is still almost non-existent. Isn't that mind-boggling? You can probably see why that I probably don't opt for playing these games too often, the lottos and the mega things and whatever. Not only because of the chances slim, but ladies and gentlemen, again, because I'm not really the luckiest person on the planet either. So my chance of winning this would probably be this divided by 1 trillion, even more, okay, or something. It's just not happening. But you know the old adage, if you don't play, then there is no chance of winning. That's the old adage, though. Okay. Yeah, true, but you probably have a better chance of having an EF5 tornado go right through your living room. And that's rare, very rare. Thank goodness it's very rare. All right, so ladies and gentlemen, we're learning about these permutations and combinations. Just look at problem number 58. This one's interesting. 58. A committee of 4 men and 4 women is to be made from a group of 12 men and 9 women. In how many ways can such a committee be formed? Well, let's look at the men. How many men do we have to choose from? How many men do we have to choose from? And does order matter in forming this committee? Do you think order matters? Is there like an office of president, vice president, treasurer? I don't see any of that. I don't think order matters here. And since order does not matter, we're talking what? Combination, not permutation. How many men do we have to select from? We got 12 men. And from the 12 men, we have to select 4 men. So ladies and gentlemen, this is the total number of ways of selecting a committee of size 4 men, choosing from 12 men. Now the women. How many women do we have to select from? Uh-oh. How many women do we got to select from? Number 58. We got 9 women to select from, and we need 4 of them, correct? Form a committee. 9 in combination with 4, or 9 choose 4. This is the total number of ways of choosing 4 men from 12 men. This is the total number of arrangements of choosing 4 women from 9 women. The fundamental principle of counting says the total number of ways of forming an 8-person committee, where we must have 4 men and 4 women, is going to be the product of these two combinations. You must multiply this by this to get your answer for problem 58. So here we go. Let's dial that up on our calculator. So this is going to be 495 possible ways of forming a 4-person committee or 4-person committee with all men on it. If we choose from 12 men. How many ways to form a committee with 4 women, choosing from 9 women if order does not matter? Well, we're going to find out. There's 126 different ways. Now we multiply these two together. We got our answer to that question. 495 times 126. The answer is there's 62,370 different committees that can be formed, where we must have 4 men and 4 women, choosing from 12 men and choosing from 9 women. There's your answer for number 58. All right. Well, these are kind of fun, actually. Let's look at number 74 here. Oh, there's so much fun to be had in this textbook. Consider the set of numbers 0, 1, 2, 3, 4, 5. How many 3-digit codes can be formed with the given restrictions? Number 74 says the code may not contain repeated digits. Ladies and gentlemen, we must have a 3-digit code, and yet we cannot have what? Any repeated digits. For number 74, I'm tempted to make 3 mailbox slots here. Now, there cannot be any repeated digits. How many ways can I fill in the first slot? Well, how many digits do I, or numbers do I have to choose from? Do you remember what that was there? The set consisted of 0, 1, 2, 3, 4, 5. So how many numbers or digits can I put in the first slot here? 1, 2, 3, 4, 5, 6. 6 digits can go in the first slot. How many digits can occupy the second slot, keeping one of the digits out for the first slot, because we cannot have any repeats. So then we only have 5 digits left to occupy the second slot. But now we keep out 2 digits, one for the first and second slot, which means we only have 4 digits left to select for the third slot. What's 6 times 5 times 4? Gives you 120. There's your answer. So there's 120 different ways to form a 3-digit code if we cannot have any repeats. No repeats. Everybody see that there? All right, let's see. Problem number 80. Social Security numbers assigned in the United States are comprised of 9 digits of the form of 3 digits for the first group, 2 digits for the middle group, and then 4 digits for the last group. Would there be enough Social Security numbers for the population of China if the Chinese used the same system, assuming the population of China is approximately 1.5 billion people? Well, do you think digits are repeated digits are allowed in Social Security numbers? I don't have any repeated digits in my Social Security number, ladies and gentlemen, so I'm just asking this question. Does anybody out there have repeated digits in their Social Security number? Anybody?
Yes, they have them.
Okay, so it is possible. I didn't know that. I learned something today. Interesting. Okay, so it is possible, I guess, to have repeated digits. All right, so we have how many little mailboxes here? Oh, by the way, remember the last problem, 74? where I was trying to form all possible 3-digit codes from the digits I had available. There were 120. I have a question for you. Is this a permutation or combination? They gave me 120. You think it's a permutation or combination? Let me ask you this. Is this code here 012 the same as the code of 210? And is that the same code as 102? Are these codes the same? Do you think these codes are the same? Let me give you an example. When you were in high school, we had a combination lock usually on our locker, correct? Does it matter in what order you crank out these digits for a code?
Yes.
It does matter. Makes a huge difference. These codes are not the same. These are different. And so here's my question. Since these codes are different, does order matter in which I occupy these 3 slots? Does order matter?
Yes.
There is yes. So ladies and gentlemen, this is a permutation. So therefore, to get this 120, we really have what? 6 numbers to choose from. 6 permuted, how many ways? 3 ways, correct? If you got on your calculator and found 6 permuted 3 ways, you would discover it's 120. So my mailbox way of doing the problem is the same way as if you just used a permutation, because order does matter now, right? Order matters. All right, so order matters there. Let's get back to problem number 80 with this Social Security thing here. 3 slots for the first group, dash 2 slots or 2 digits for the second group, dash 4 digits for the last group. How many different Social Security numbers are possible if digits are allowed to repeat? Well, I have a question for you, ladies and gentlemen. How many digits can we use to populate each of these little slots or mailboxes here? 0 through 9, do you agree? The digits of 0 through 9. So that's 10 digits. So it seems to me this would be 10 times 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 10. 3, 5, 9. So that's 10 to the what power? 10 to the 9th power, which is really 1 what? Isn't that 1 billion? 10 to the 9th power, 1 with 9 zeros. Do you think that would be enough unique Social Security numbers to handle the population of China? Well, they told us the population of China is 1.5 billion. So it looks like we might be a little short here, correct? Because it looks like there's 500 million people more that are unaccounted for. Now, so it doesn't look like this system would work in China. They would have to go to maybe adding another digit. Do you agree? Maybe another digit to allow for accommodating the 1.5 billion people that need a Social Security number over there. If they even have Social Security numbers over there in China, I don't even know if they do. I'm assuming, we assume that if they did go with that same system we got in this country, yeah, we would run short. That's not enough. That's 500 million people left without Social Security cards. So that that is an issue, obviously. Okay, so that is 1 billion there. And let's see here. So all right, so yeah, it doesn't look like there would be enough Social Security numbers to accommodate the people in China there. All right, now I have worn out my welcome today. Ladies and gentlemen, there's no way I'm going to get through section 8.7, which is intro to probability. Okay. Therefore, what I'm going to do is I'm going to attach on Canvas a video that I used in the fall semester for my 130 class. The video is not that long. It will go through 8.7, Introduction to Probability. I will put that link on Canvas and you can watch it, at your leisure anytime. But please do take some time out to, take in that video. Next Tuesday, this Tuesday coming up, I will finish the lecture portion of Math 130 by going through the binomial theorem in section 8.5. That lecture will either be live or it will be a recorded video. I don't know yet because I don't know, the time in which the surgery is to be done for my wife. So I don't know the timetable on that. But either way, if I'm not live, you'll know, and I'll just send you an email to remind you that, try to send you an email confirming like whether it's going to be a live session or not. I mean, if it's not a live session, obviously I cannot hold you accountable for your attendance, so I'll just have to mark you present. Okay, so don't worry about that. All right, so I will stay on the line for a couple more minutes. If there are no other questions or concerns, ladies and gentlemen, you have a great weekend. And we are in the home stretch of this course here. So I'll let you go.